The train, one of our safest forms of transport. Over 40 million people in the US alone travel by train each month. But in a split second, a train can turn into a death trap. When disasters strike, we want to ensure they'll never happen again. It's a challenge that falls to crash scientists. This is the story of a science that deals in destruction, but ultimately aims to deliver us from disaster. This is one of the world's safest trains. In 25 years of operation, it has carried over 1 billion passengers. And in all that time, not a single person has been killed during high-speed operation. It is the French TGV. The TGV is also the fastest conventional train on the planet, capable of a blistering 515 kilometers an hour. It weighs up to 484 tons and uses a mammoth 8,800 kilowatts to propel it along the track. This marriage of power, speed and safety is an impressive feat. The TGV is one of crash science's proudest achievements. Trains haven't always been this safe. Passenger rail kicked off with a tragic accident. At the launch of the world's first intercity passenger railway in England in 1830, the train claimed an early victim. The locomotive rocket ran a spectator down and killed him. Designers hadn't even thought to equip the rocket with proper brakes. Since the early days, crash science has revolutionized the way trains are designed, making them the safe form of transport they are today. A modern train is built to protect people even in the worst of circumstances. The TGV has, in the past, derailed while running on its high-speed lines at close to its maximum operational speed of 320 kilometers an hour. But most of those on board have walked away uninjured, and no passenger has died. In an age in which trains have to compete with planes to be both fast and safe, the TGV is the ultimate in rail transportation. It's taken decades of work in the field of crash science to get to where we are today, and a head-to-head battle with the most basic laws of physics. The train is our heaviest form of land transportation. It has a high inertia, or ability to resist acceleration, so it takes a significant force to get it moving in the first place. As the train accelerates along the track, it's gathering huge amounts of kinetic energy, the energy of motion. The heavier the train is and the faster it's going, the more kinetic energy it has. The problem is, this energy is indestructible. In order for the train to stop, it has to be dissipated during the braking process. It takes a TGV from its maximum speed 3.5 kilometers to come to a halt. But if a train crashes or stops suddenly and there's no time to brake, the kinetic energy has to go somewhere. Its most immediate escape route is the train structure itself, which it will crush, bend and destroy until it has finally been absorbed. The challenge for crash scientists is to find ways of controlling this kinetic energy in a crash and protecting passengers from the destruction it can cause. The first wall of defense is the train's outer body. In the wooden trains of old, this merely protected passengers from the weather. In a crash, it would simply disintegrate. An accident in France in 1933 was a grim example. The day before Christmas Eve, in thick fog, a locomotive hit a slow-moving wooden passenger express from behind and managed to plough through almost its entire length. The locomotive reduced the wooden cars to fragments and killed a staggering 230 people. The accident was the worst peacetime France had ever seen, and it kicked crash science into action. In 1937, scientists began a set of full-scale crash tests to investigate what went wrong. They sent a 260-ton train traveling at 39 kilometers an hour into some wooden rail cars. As they watched, one car sliced through the entire length of another. An awesome level of destruction. A closer examination reveals exactly what's happening. As two rail cars collide, their heavy underframes meet. The kinetic energy of the moving car forces one underframe over the other, then propels it into the weaker wooden car body above. In seconds, the kinetic energy of the moving train has been dissipated in the complete destruction of an entire rail car. This deadly phenomenon is called telescoping, because the way the cars slot into each other looks like a retracting telescope. Telescoping was one of the greatest causes of death and injury in train crashes at the time. Scientists were desperate to find a way of preventing it. The tragic truth was, a solution already existed. In 1916, pioneering railway designer John Robinson invented a set of corrugated metal plates to be fitted to the end of each railcar. In a collision, these would lock together and prevent one underframe rising over the other. The interlocking plates channel the kinetic energy horizontally and prevent the vertical movement that can develop into telescoping. Today, modern versions of Robinson's metal plates, known as anti-climb devices, are a standard safety feature on many trains. But at the time they were invented, they just didn't catch on. Crash scientists were busy looking elsewhere for an answer to the problem of telescoping. The French decided to fight force with force and built a new, more rigid metal-bodied railcar, complete with reinforced ends to repel the impact. They put their new design to the test. The metal design clearly fared better than its wooden partner. It deflected the kinetic energy and emerged relatively intact compared to the ruin of the wooden car. Wooden cars were phased out through the first half of the 20th century, and metal ones introduced in France and across the world. So, was the introduction of the metal railcar a turning point in rail safety? Unfortunately not. Crash scientists failed to realize that by solving one problem, they had merely created another. By the 1950s, metal railcars had more or less replaced wooden ones on the world's railroads. They were sold to the public as the latest in luxury. Crash scientists hoped that, with their stronger design, they would save lives too. But hundreds of people were still dying in train wrecks.
How many bodies, how many shattered hopes still lie beneath the twisted wreckage? No man can estimate, until the last of the grim debris has been cleared.
Telescoping was merely being replaced by a new and equally deadly phenomenon: overriding. The problem cast a shadow over the railroads for decades. In 1988, 3 morning rush-hour trains collided after a signal failure near one of Europe's busiest rail junctions at Clapham in England. Survivors witnessed the terrible consequences of overriding.
One train overran the other train and there were people underneath and really badly hurt.
So we've had limbs severed, bodies cut in half. We've had a brain, just a brain, brought to us on its own from a shattered skull. These are the sort of injuries you get in collisions.
35 people suffered horrific deaths. A closer analysis reveals why overriding was such a killer. When one metal car hits another, the rigid body and inertia of the impacted car can provide a strong opposing force. In these circumstances, the moving car's kinetic energy tends to carry it all the way over the car in front. It will then come crashing down on the roof and passengers below. In an effort to address the problem of overriding, crash science would need to take a radical step in a totally new direction. In its early days, crash science concentrated on finding ways to improve the strength of trains. The guiding principle was that they should be built to resist deformation or buckling. Modern crash science, however, operates according to a fundamentally different principle. It looks for methods to encourage deformation. The idea was first introduced in the 1950s by crash scientists in the car industry, who came up with the idea of the crush zone, an unoccupied area in a car specifically designed to collapse in a crash. Its function is to absorb the impact, soaking up the kinetic energy before it causes more serious damage to the rest of the car and its occupants. The crush zone is sacrificed so that the passenger area remains intact. In the 1980s and 90s, crush zones were finally investigated as a possible answer to the most pressing problem in rail safety: overriding. In response to the Clapham disaster, scientists launched a £4 million research programme. The problem was how to adapt the concept of the crush zone for use in rail design. Professor Rod Smith worked on the pioneering project.
I recall visiting Paris and travelling on the metro system. And as the train pulled into a station, two huge adverts on the side of the tunnel wall caught my eye for plastic drinks bottle containers, one of which was shown full, as it would be when it was full of water, and the next one was shown as it was compacted into a neat little heap to take up very little space in one's waste bin. And it was clear that this compaction had been achieved by clever design of the bottle, which was exactly the sort of design that we needed.
What was intriguing to the scientific eye was how the bottle's design incorporated weaker and stronger areas. So as it's crushed, it folds up in a predictable way.
The bulk of the deformation has taken place in this little zone here. All the energy has been absorbed in the folds in the bottle. This is exactly what we want to achieve in compressive members in the crash-worthy design.
The work of Professor Smith and his team was finally put to the test in October 1994. Conventional rail cars were equipped with crush zones at each end. Inside these were metal structures triggered like the bottle to collapse in a predictable way. On the outside were modern versions of the devices John Robinson had invented nearly a century earlier, the corrugated metal plates, now called anti-climb devices. Crash scientists hoped to prove that these simple design alterations could prevent overriding. Their theory was that during the collision, the anti-climb devices would lock together, preventing any vertical movement. The kinetic energy would have no option but to travel into the crush zone, where it would be safely absorbed. The moment of truth was the final crash test. 2 complete trains were equipped with a multitude of the latest devices to measure loads, accelerations, displacements, and strains. All in all, 250 channels of information for the scientists to analyze after the event. The crash test itself could only happen once. The impact lasted a mere 3/4 of a second. The test was a success, as crush zone after crush zone collapsed in the way it was designed to. The energy was progressively absorbed right along the length of the train. Footage showed how the anti-climb devices locked together perfectly. The bending and buckling of metal in the crush zones dissipated the energy before it could reach the passenger areas. These were undamaged, and there was no overriding. In the UK, the fitting of crush zones and anti-climb devices became mandatory on all new railcars. In the US, crash scientists were watching. America was developing her passenger rail network, and too many rail accidents resulted in dramatic destruction. In 1987, 16 people were killed in a crash near Chase, Maryland, when a freight train missed a stop signal and was slammed by an Amtrak train at 206 kilometers an hour. The front cars were completely crushed as they careered sideways into each other. It was time to take a good look at safety. The US Department of Transportation invested $25 million in a rail safety program that moved America to the forefront of crash science. The US tests addressed a particularly American problem. Typical passenger cars on the US railroads derive their design from the old railway post office cars of the early 20th century. These were built strong and heavy, with rigid linking mechanisms or couplers between them. They needed to be able to resist daily bumps and shunts from the heavy freight cars they'd normally travel attached to, and protect the postal workers sorting the mail inside. This inherited design makes the American passenger car particularly prone to a dangerous crash phenomenon: jackknifing, or as it's technically known, lateral buckling. Crash scientists at the Federal Railroad Authority conducted a test in April 2000 to examine the phenomenon. 2 cars of conventional design were sent into a wall at 42 kilometers an hour. Most train collisions occur at these lower speeds. Upon impact, there was a jostling movement between the cars. The back car shifted slightly to the right and the front car to the left. Both cars derailed in the process. As the cars collide, they're already slightly misaligned, and the energy of the impact makes them kick out even more. At higher speeds, when there's more energy involved, this movement is much more exaggerated, and the cars zigzag out in different directions. The danger is railcars will smack into each other side on, and the weaker side walls will collapse inwards, crushing the passengers inside. Crash scientists already knew the horror this could result in. Crashes such as the one at Chase, Maryland, had provided them with grim examples. Could crush zones solve America's rail problem of lateral buckling as well? There was only one way to find out. The 2 test railcars were once again sent into a wall at about 47 kilometers an hour. This time, they were equipped with specially designed crush zones. The difference was subtle, but significant. As the 2 cars collided, there was none of the sideways jostling seen before. Inside the crush zone, this is what is happening. The coupler which links the 2 cars retreats backwards, crushing in on itself. The energy is absorbed, and the railcars stay in line and on the track. The American testing program proved that adding crush zones and collapsible couplers to existing railcars reduces the risk of lateral buckling. British and American crash science has developed methods of making old train designs safer. Another approach is to scrap the old design and start from scratch. This is what the French did 25 years ago with their launch of the TGV. At the time, the world's fastest trains ran at 200 kilometers an hour. The builders of the TGV wanted it to run at 260 kilometers an hour. Such a huge jump in speed called for a huge conceptual leap in train design. The TGV's designers came up with a revolutionary idea: an articulated train. Instead of each railcar having its own wheeled undercarriage, undercarriages are shared between the cars. This means one car simply can't move independently of the others. The vulnerable point at which the two cars are linked is now strong and stable and won't buckle either sideways or vertically. The problems of lateral buckling and overriding between cars should be eliminated. Great in theory, but would it work in practice? In a test in 1994, 2 TGV railcars were crashed into some stationary cars at 45 kilometers an hour. All of the cars were weighted down with ballast, so that the energy in this collision was equivalent to a TGV hitting an 80-ton truck at 110 kilometers an hour. The articulated underframes behaved with perfect stability, and there was no suggestion of lateral buckling or overriding. François Lacote of Alstom Transport was the man officially in charge of bringing the first TGV into service. He's now Senior Technical Vice President at Alstom.
The key thing is that the train remains in line, remains completely integral, instead of, I should say, a classical train where the different pieces of the train, the different cars could completely go everywhere outside.
The result is that by limiting and controlling the movement of railcars in an accident, you limit and control the movement of passengers inside. It's a basic principle that has saved lives. In 1993, the TGV derailed at a phenomenal 294 kilometers an hour. It remained perfectly upright and in line, and only 2 passengers were slightly injured. The TGV is a huge success story. A train which reconciles the conflicting demands of speed and safety. At the engineering company Alstom, work is underway on the fastest and safest train in the TGV family yet. The AGV is still in its design phase. It's a train which encompasses the most cutting edge in crash science, combining an articulated design with the latest crush zone technology. Here we're looking at the manufacturing of the energy absorption structure which goes inside the train's nose. It can absorb a massive 6 megajoules of energy if the train's in a head-on collision. That's the same amount of energy a large automobile would hit the ground with if dropped from the top of the Eiffel Tower. The absorption structure works according to exactly the same principle as the plastic bottle. The way it crushes is controlled by means of weaker and stronger points in its design. The development of the energy absorption structure for the AGV's nose took a whole year. The process started with computer-aided design and then progressed to the development of numerical simulations, which predict how the structure will crush in a collision. This was followed by actual testing, for which the engineers at Alstom had to build a new crash science device. With limited space to operate in, they needed to find a way of generating speed over a very short distance. So they invented a huge gun, which fires out a heavy cart, which then crushes the structure being tested. The gun is capable of accelerating an object of 60 tons from 0 to 50 kilometers an hour over a distance of just 3.5 meters. In this way, the structure which goes inside the AGV's nose has been tested to check that it crushes in a controlled way. Alstom is confident the AGV will meet the demands of a safety-conscious 21st century. Over the last few decades, crash science has come a long way. From the wooden carriages of the early 1900s to the highly sophisticated design of the TGV, the exterior design of trains has been transformed. But that's only half the problem. What happens inside a railcar during a crash is just as critical as what happens on the outside. In recent years, crash science has addressed this new and challenging frontier. It's much more difficult for crash scientists to analyze how the human body fares in a train collision than it is for them to examine how train structures will react. For one thing, the human body is a much more complex structure than your average train. For another, while there are plenty of spare train parts for scientists to crush, bend and destroy, people who are willing to be crash tested are in short supply. The crash test dummy is one source of information on what actually happens to people in collisions. Another invaluable source is crash victims. People who can tell you exactly what it's like to be hurled against the inside of a train during an impact. In October 1999, at Ladbroke Grove in London, England, a passenger train missed a stop signal and collided head-on with another at a combined speed of 209 kilometers an hour. Jonathan Duckworth was a lucky survivor.
It was quite an extraordinary experience, being thrown about, bumped about in your seat with things flying around the carriage. Everything that had been on the table in front of me just disappeared. I've never seen so many bruises. There were bruises all over my legs, all over my back, arms, because of this incredible, it was like being in a tumble dryer, really.
Rail disasters often lead directly to advances in safety. It's a phenomenon that's been called tombstone technology. A collision in Placentia, California in 2002 is just such an example. A freight train missed a signal and smacked into a passenger train head-on. 2 people died from hitting the tables in front of them. The US Federal Railroad Authority snapped into action, determined to find out how something as seemingly benign as a table in a rail car could kill. They decided to make use of the most cutting-edge technology. Meet the Hybrid 3 Rail Safety Anthropometric Test Device. The world's only crash test dummy developed specially for use in the rail industry. Worth nearly $500,000, he's the most sophisticated dummy in the world. The rail crash test dummy's first experience of a full-scale crash test was at the Federal Railroad Authority's testing facility in Colorado. The test would shed light on how the Placentia rail crash victims had died. Footage reveals that as the railcar collides and is brought to an abrupt halt, its kinetic energy is transferred to the dummy. The dummy continues moving forwards until he's stopped by a secondary collision with the table. The dummy's lower ribcage is the critical, crushable point at which the energy of the impact is finally absorbed. As pressure is applied, the ribs fracture. the internal organs can be punctured and lacerated as they're pushed against the spine and broken ribs. Injuries to organs like the liver and spleen are extremely dangerous. In this test, the dummy records serious to life-threatening levels of injury. The Federal Railroad Authority has recently tested a new design for a safer table. On impact, the table crushes, absorbing the passenger's kinetic energy. It's a less severe blow to the passenger's abdomen, and there's a much reduced risk of serious injury. There are already plans to introduce these safer tables into new American commuter trains. The FRA's tests also show that the safest place to sit is with your back to the direction of travel. In an impact, the dummy has only a tiny distance to travel before the secondary collision occurs between him and the seat back. Minimal levels of injury are recorded. Forward-facing passengers are at greater risk. They have further to travel before they hit something. Every split second that they're moving, they're gathering kinetic energy and building up to a more severe final impact. They can suffer serious head and neck injuries from hitting the seat in front of them. If they fly over the seat in front, the final impact will probably be even worse. This discovery has led to experts questioning whether to introduce seatbelts on trains. It's an issue that still divides. Dr. William Harrop Griffiths has witnessed the results of a rail crash firsthand.
Most of the injuries in a train crash are blunt injuries. There are people in a train that suddenly stops, and let's say the patient's going at about 60 kilometres an hour. They're going to carry on moving if they're not restrained until they hit something. Just as a doctor who's seen a lot of injured people, I think I would rather wear a seatbelt.
Safety experts like Rod Smith argue that seatbelts are an impractical solution.
I have doubts, partly because of the cost of fitting them, partly because of the difficulty of maintaining them, and partly because accident statistics suggest that the saving of lives would be few compared with the disbenefits and the inconvenience and the loss of comfort to passengers of using them.
For now, the debate over seatbelts continues, and they have not been installed as a standard safety feature on trains. Jonathan Duckworth had nothing to restrain him during the massive impact at Ladbroke Grove, where his railcar overturned. His experience highlights another major safety issue: emergency evacuation.
There was a bit of panic because there was people saying fire, and then there was just no idea, how do you get out? The turning over of the carriage has completely thrown apart my sort of awareness of where I was.
At Ladbroke Grove, rail passengers found themselves trapped. Some lost their lives in the fire that followed the collision. Professor Edwin Galea is an innovative crash scientist who was spurred into action by the Ladbroke Grove accident. He conducted groundbreaking research into the issue of emergency evacuation.
What Ladbroke Grove highlighted was how difficult it is to evacuate from an overturned rail carriage. Up to the Ladbroke Grove incident, no work had been done to quantify, to understand, to measure, to observe how people can evacuate from an overturned rail carriage.
Professor Galea and his team ran a full-scale evacuation test. They flipped a conventional British railcar onto its side and placed 32 volunteers inside. They blocked off one end, introduced smoke to obscure people's vision, and challenged them to evacuate as quickly as possible.
An overturned rail carriage is a very challenging environment to be in. It's very confusing to the individuals. What was the floor and the ceiling are now the sidewalls, and what were the sidewalls are now the ceiling.
The doors that you get on normally It would be like opening a hatch in a submarine if you could actually reach them, because they were way up, and they'd been far too heavy for the passengers to open them. There were briefcases and coats and seat cushions, just a sort of sea of seat cushions all over the place. I'm reasonably fit and quite tall, and for some of the people it was, particularly injured people and the ones who are less mobile, very, very difficult.
Professor Galea's test provided the first scientific data to back up the testimony of rail crash victims. Proof that it can be incredibly difficult to evacuate an overturned rail car within a time frame that's considered safe if there's fire.
2.5 minutes is typically the time that we would expect to empty an enclosure subjected to fire. If you are still in the enclosure after 2.5 minutes, it's likely you're going to die as a result of being exposed to the fire products.
In the evacuation test, it took a full 7 minutes for all 32 passengers to escape the car.
It's very worrying.
Professor Galea believes the answer is to change the interior design of rail cars. To build luggage racks like the ones in airplanes, which contain their contents. To mount pop-out windows. And to install ceiling hatches, which provide an easier escape route if the car ends up on its side. He believes train companies have been slow to adopt these innovations.
Unfortunately, we don't have ceiling hatches in the trains, and I'm not aware of ceiling hatches actually being implemented anywhere around the world. There are a lot of issues that need to be looked at in more detail and implemented within our rail rolling stock.
Interior design is an area of ongoing research in crash science, but this still only addresses the safety of people inside a train. In America, during the first few months of 2006, most victims of train collisions were people who weren't on the train in the first place. 99% of all deaths occurred when people strayed onto the track, often jumping the warning lights at crossings and caught in the path of an oncoming train. And with nearly 240,000 highway rail crossings across the US, almost everyone has the chance to become a fatal statistic. Collisions between trains and road vehicles have inspired crash testing of a slightly different kind. Railroad companies have staged crashes and invited the public to come along and watch. The aim is not to entertain, but to raise awareness about the dangers of railroad crossings. In this crash test, a freight train weighing over 1,000 tons plows at 53 kilometers an hour into an empty school bus. Measuring devices record a force of 200 G at the point of impact. The bus is being buffeted by a force 200 times its own weight. A train hitting a vehicle is, in terms of force exerted, equivalent to a car hitting a sparrow. The intention is to frighten people into paying attention to the warning lights at crossings and staying well clear of oncoming trains. Crash science has developed technologies to cope with or even eliminate the most common kinds of rail accident. But what about those less common crashes, rare but deadly? Crash scientists have for years been doing everything they can to address the threat of a collision involving a train with dangerous cargo on board. Crash scientists aim to ensure that if a train carrying hazardous cargo crashes, the risk to human life is as low as possible. The stakes are high. This kind of rail crash has the potential to kill more people than any other. In Mississauga, Canada, in 1979, a freight train carrying deadly chlorine gas derailed and exploded. 218,000 residents were hurried to safety in one of the largest peacetime evacuations in North American history. second only to the 2005 evacuation of New Orleans. In the end, there were no fatalities, but the lives of nearly 250,000 people had been put at risk. Crash scientists across the world have conducted tests to ensure they're prepared for accidents involving dangerous cargo. In this crash test in the UK, a train was sent at 160 kilometers an hour into a deliberately derailed nuclear container to see if it could withstand the impact. The container cost £500,000 and was made of 50 tons of steel with 14-inch thick walls. It had already been subjected to a series of impact experiments. But this would be the final test. The crash looked devastating. But the important thing was that the nuclear container emerged intact. Its strong walls simply deflected the kinetic energy. When the impact test was complete, the experts checked the pressure inside and confirmed that there was no significant change. Crash scientists were able to reassure the public that manufacturers had built a container that could withstand the ultimate disaster. Work continues in the field of crash science to provide every possible safeguard in every imaginable type of train crash. But crash science does have its limits. It can't protect us against everything. Its biggest enemy is, and always has been, speed. As quickly as crash scientists try to improve the safety on our trains, so engineers and designers try to make them lighter, smoother, and above all, faster. It's a route that sometimes leads to tragedy. In 1998, one of the world's fastest and most technologically advanced trains, the German ICE, ended up in ruins. It derailed because of a damaged wheel, crashed at 200 kilometers an hour straight into a bridge, and disintegrated in the impact. 101 people were killed. Even a train of the very latest design doesn't stand a chance in a high-speed crash with a concrete bridge. Experts judge that no amount of improvements to design or strength could protect a train in such a massive impact with a solid object. As trains get faster, it's no longer enough to improve the way they cope in an impact. In recent years, the emphasis in crash science has moved to developing high-tech means of avoiding accidents altogether. Traditionally, train operations are controlled via signaling systems. Lights along the track tell the engineer when to stop and when to go. For the TGV, this system has been developed into something more sophisticated, specifically tailored for high-speed operation.
When you are running at very, very high speed, it's no longer possible to ask the driver to look outside the driver's cab on the track to see the colors of the signal. So we had to design a very safe system where the signaling equipment is no longer on the track but on board.
Information is transmitted as electronic signals from a control center into the rails. These are then picked up by antennae under the train. They're processed by onboard computers and displayed to the engineer in his cab. They tell him what speed he should be traveling at to maintain a safe distance from other trains. If the engineer fails to respond to an instruction, the train's computers have the ability to take over and bring the train to a safe stop. The trains of the future will be operated within even more stringent accident prevention systems. This is the Trans-Rapid Maglev. being tested in Germany. Maglev is short for magnetic levitation. This train rides on a cushion of air, created by an electromagnetic reaction. It's a case of electronics replacing mechanics. One set of magnets draws the vehicle towards the track or guideway from below. Another holds it laterally on track. An electronic control system keeps the train levitating at a constant height of 10 millimeters. The maglev is propelled and braked by electromagnetic reactions too. There's no contact with the guideway, therefore no friction, which means this train can reach speeds of up to 430 kilometers an hour. In this case, faster is definitely safer. Guideways can be built over roads to avoid the need for road crossings. And the trains wrap around the guideway, so it's virtually impossible to derail. So, are crash scientists close to creating a perfectly safe train? Recent history demonstrates that perhaps this is an impossible goal. The world's worst train disaster occurred on December the 26th, 2004, when a train was simply swept off the rails by the South Asia tsunami, killing as many as 1,700 people. And as the terrorist atrocities in Madrid and London testify, we have yet to build a bomb-proof train. There are challenges ahead for rail crash science, but the achievements so far have been considerable. Trains are one of our safest forms of transport. European statistics put them equal in terms of safety with planes, and roughly 20 times safer than cars. In the US, for roughly every 3.5 billion kilometers traveled by train, only a single passenger dies. The terrible potential this huge, heavy, fast form of transport has for mass destruction has, to a large extent, been harnessed. The story of rail crash science is the story of man's triumph over metal.